There's a lot to talk about when we dive into functional analysis. It is a huge topic that many undergraduates in math just find hard and struggle with, and even people who are good at it don't understand it fully. But here's what we're going to try to do. I want you to be able to pick up a textbook on functional analysis at the end of this video and actually be able to understand it and enjoy solving the problems. So let's begin. Functional analysis works with mostly spaces that are inner product spaces. So here's a handy Venn diagram. I forget what these things are called, but it's just sort of showing you the how these things are topologic, how they are arranged in a hierarchy. We are going to talk about normed vector spaces, which is the topic of this video right now. Yeah, and vectors, everyone's favorite topic from maths. So functional analysis is like a marriage between linear algebra and analysis. So yeah, we're going to use vectors a lot in this video, in this course. The other thing we're going to talk about a lot is norms. Now, norms in its most basic sense can be understood as the measure of something, like the magnitude, usually a function or some polynomials or anything like that. Norms are really useful in helping us determine also the distance between two things in a set. So they're very important in this course. And obviously, infinite dimensions, because functional analysis is all about taking linear algebra and making it in an infinite space. Now we're going to understand soon, hopefully, what that means. But first we have to understand a very important topic, and that's Cauchy sequences. All right, let's imagine you have a sequence of numbers x1, x2, x3, and so on. It could be finite, it could possibly be infinite, maybe it terminates, we don't know yet. Now, the first thing we want to do in analysis is we want to have a rigorous definition of what it means to converge. Let's go. For any epsilon greater than 0, there exists a positive integer big N such that if m, n are greater than or equal to big N, then the absolute value of xm minus xn is less than epsilon. Now, it's a bit of a mouthful to take in at the moment. So let's go and explain it via some crappily drawn stick figures. All right, imagine we have two friends, Alice and Bob. Bob wants to play a game with Alice. He goes first. He picks a number epsilon. That's a positive real number, something that's like something that can be square root of 2 pi, 0.001, or 0.9 repeating, whatever. It has to be small and positive. Now, he picks an epsilon 0.1, and now it's Alice's turn. And she has to pick a positive integer. That is like a number that doesn't have any decimals. It's not negative. She has to pick a number that's something like 5 or 10 or 100. All right, she picks n as 5 because she thinks she's got it. Now, this number, what it's going to do is it points to a particular part of the sequence of numbers that we had established before, where n is the number you stop at if you're counting the sequence. So if Alice said 5, then we would stop counting at x sub 5. And what happens now is we've stopped at x sub 5. So we need to subtract x sub 5 from x sub 4, and we see the absolute value of that difference. That is only the positive side of that number. And we see if it's less than the epsilon that Bob chose. Remember, the epsilon was a small positive real number. And if that holds, then Alice wins this round. Then Bob goes again, and Bob picks an even smaller epsilon, something that's like 0.0001. Now Alice needs to try harder. Alice needs to pick an even bigger n, Alice picks 100. And maybe she succeeds this time too, because x sub 100 minus x sub 99, remember, it's always the number we stop at is the end that Alice picks, and then we subtract it from the previous one next to it. So it would be x sub 100 minus x sub 99. And if that number, again, if the positive side of that is less than epsilon, then Alice wins again. Now, what are we actually doing here? If for, I don't know, an infinite amount of time, Alice and Bob just keep playing this game and Alice keeps winning, what that means is no matter how big an n she picks, she can always get the positive, she can always get the difference between those two consecutive terms to be smaller than the epsilon Bob picks. And what this means is that the numbers, as you go further and further down the sequence, they're getting arbitrarily closer and closer together. And eventually they'll get so close to each other that they'll become one number. So we will converge into a limit. And that's basically what it means to be Cauchy. So when you have a sequence of numbers, and if after a finite amount of time that you keep going further and further down the sequence and the number converges to a limit based on this definition of epsilon and n that we've given, then we say that the sequence is Cauchy. So we've got that. That's a very important tool in analysis. What that allows us to do is to observe the properties of mathematical functions and be able to do things with them, and they will behave well enough for us. All right, cool. Now we can get to Banach spaces. Banach spaces are basically vector spaces equipped with norms. And vector spaces are just basically sets which contain vectors, and you can do mathematical operations with them, like addition, multiplication. You can scale them. You can do a lot of things. We're not going to go into vector spaces right now. That's something for linear algebra. And we already told you what a norm was before. So now we can, now that we know what a Banach space is, that's a vector space with a norm, we can try to attempt a question from an undergraduate level course on functional analysis and actually prove that a specific space is a Banach space. And all we needed so far was our definition of Cauchy sequences and our previous knowledge of what vectors and norms are. So let's go ahead. All right. So we've been given this question. X, which is a space, contains functions that map numbers from an interval on the real number line, that is from A to B, and they map it to a space K. Now, we're gonna talk about what K is later. We have the additional information that F is bounded, and we're given that in this space, the norm of F is the supremum of the absolute value of F when evaluated on X. Prove that X is a Banach space. All right, it's more doable than you think it is. We just have to go step by step. First, what is K? Don't worry about it. K might look scary, but K is just the real numbers and complex numbers merged together in a way. It just means that whatever output we get is either going to be a real number or a complex number, and it will behave with the properties of a real number or a complex number. So our function takes an input from the real number line, some interval, and just gives another real number or complex number out. F is bounded. Means F will not go above or beyond a certain range. F cannot exceed certain limits. F will remain bounded, of course. All right. So now let's do something really cool. We know what Cauchy sequences are. Now let's apply those to functions. Let's have a sequence of functions. And these sequences of functions, if you really want to understand what a sequence of functions is, just for example, take the function x to the power n. So f1 would be x to the power 1. f2 would be x to the power 2. f3 would be x to the power 3. So on and so forth. So as the powers of f increase, as the sequence of f increases, the powers of x increase. So the function is just basically something like that. So we have fn, we assume it's a Cauchy sequence in X. And then for each epsilon greater than 0, there exists some big N from natural numbers such that nm greater than or equal to n. It means that the norm of fn minus fm is less than epsilon. See, this is really similar to our previous definition of Cauchy sequences, so there's nothing to be afraid about. Now, what we're doing here is we're assuming certain things about our sequence of functions, and when we assume those to be true, we're going to take them to their natural conclusion and see if it all makes sense. That's what maths is all about. All right, when we have, we've got a series of functions. So for any x naught taken from the interval a to b, we have that when those functions, the series of functions are evaluated at that number, it will still follow the Cauchy principle. That is, for any epsilon, the difference between fn and fm when evaluated at x naught will be less than epsilon. And this means that fn x naught is a Cauchy sequence in K. So simply put, if you have some sort of input, some x, some number we chose from the real number line, from that interval on the real number line, and we evaluate it in the function, in the series of functions we have, we see that as you go further down the series, these functions get closer and closer together. That means that they will eventually converge to one function which will give the same output for the same input that's given. That's x naught. And we have that this is a Cauchy sequence in K. Another important information about K. K is complete, which means that any Cauchy sequence that converges, it will have its limit within that set that the sequence is from. So it means everything is contained within K. It cannot go outside of K, which is good. So if every Cauchy sequence in a set also has a limit in the same set, then we know it's complete. All right, so we have all our definitions before. Now, what we said before was that when we assume that our fn's get closer and closer together because the difference between them is less than a certain epsilon, that means they will converge to a certain function. And we can see that here when we say that f of x naught is equal to the limit as n goes to infinity to fn x naught, which means that eventually when we have n as it gets bigger and bigger and grows larger, it converges to f. It becomes the function f. All as far as down as you go, all the functions will be the same. And that is for any x naught picked from A or B. Here we just do a little bit more busy work and we establish what we just said previously, which is that if you take m to infinity and n as it grows larger and larger, eventually we can say that fn x naught minus f of x naught will be less than or equal to epsilon. So here we're just taking things to their natural conclusion. We're assuming that m goes to infinity, and we're saying that if you subtract any function from that sequence, any n, minus the limit of that function, which is f, you will get something smaller than epsilon. And since we picked any x naught from the interval, and it was arbitrary, this will work for any function or any input we take. So now we can come and wrap things up. So we say that the norm of fn minus f is equal to the supremum of fn x naught minus f x naught. Now supremum basically, for all intents and purposes right now, just means the maximum. So that just means the maximum value that these functions can produce. That's what we're going to take from this equation. So now that we have proved that fn will converge to some function f in x with n big enough to become n, then that function and the sequence of functions belongs in that set. So that f is basically part of the space X. So we used everything we had from the question. The fact that we have a sequence of functions, they're all bounded, and they map to a space K. and K is complete. And we know that since our functions behave nicely and they converge to a single function in K, that means that they must all be Cauchy. And if they're all Cauchy and they all have their limits within that set, then X surely must be a Banach set. And since we proved that this works for any arbitrary X, that means you can choose any number and get to that desired result. Thank you a lot for listening to me. And if you have any questions, please let me know in the comments.